Hello, everybody. So this is time to do or go into multivariable integrals or multiple integrals, all right? So this is the video for section 5.1 in your OpenStax book, Calculus 3. And so we go right into double integrals, but in section 1, we will restrict our domain to rectangular regions, all right? In section 2, we go into more general regions. All right, but again, the fundamental to the idea of double integrals is how to integrate over rectangular regions. All right, so let's get started. Okay, so section 5.1, oops, not the right thing here, is on double integrals over rectangular regions. All right, so you know the regions can be, anything like this, or it could be a circle, or, it could be a whatever, right? This time we are just focusing on rectangular regions. The reason, and it doesn't have to be here, the reason is because for rectangular regions, we can have A and B and C and D all fixed numbers, right? And so once you learn how to do that, then we can go into more complicated regions, all right? So let me go ahead and get started, not with E, but let me get started with the idea of the double integrals, since now you know all about what integrals are, right? Integrals are just continuous sums, right? All right, so we define this integral, right? By the way, when we have this idea of dA, right? So if you have any kind of region, let's say you have a region R, right? And it doesn't have to be rectangular. What we do is we divide this into a bunch of smaller pieces like we did before. And this region, the area of the ith rectangular region is the called delta AI, right? And as you can see, if these are divided into small rectangular pieces, basically the area of a rectangle is, of course, the length times the width. And so this will be just delta xi times delta yi, or vice versa, right? So dA in our case will be dx dy or dy dx. And it doesn't matter which order you do this, because after all, the integration can be done in either order according to Fubini's theorem. All right, so this, I can write this as dy dx, okay? But I want you to pay attention to this carefully, right? So what we have here is we have a function defined on all xy points xy, right? And here, y is the one, you see that, this first one here, you go from inside out when you evaluate integrals. Y goes from C to D. So here's C, here's D, right? And X goes from A to B. Oops, right? So that's what this double integral is indicating. So in terms of the graph or in the region, this is a region, and you definitely need to learn how to sketch the interval or the region over which you are integrating a function, right? So in this case, if you are given A, B, and C, D, where A, B belong to the x-axis and the C and D belong to the y-axis, you need to be able to visualize that your region of integral or integration is this region. Okay, now you can switch the order, and you should learn how to switch the order. If this is still the region that you want to integrate, okay, you should be able to switch the order in this way. It's still f of xy, but if you switch the order, of course, it becomes dx dy, right? And the bounds for x has to be right here. So AB is here. And for bounds for y should be outside. Right, and so these are the things that you have to adjust every time you take the integral. And also, I should mention, just write this as a note. Okay, maybe I should do an example first. Yeah, let me do an example first before I go to this note here. All right, so here's an example. Right, the integral from 0 to 1, and then 0 to 2, f of xy dy dx, okay? Is this question mark equal to 0, 1, 0, 2, f of xy dx dy. What do you think? Okay, notice here, you have to pay attention to all the details here, right? So here, the order is dy dx, and here, the order is dx dy, right? Are they equal to each other? Well, let's compare. See here, what we are saying is x goes from 0 to 1. Y goes from 0 to 2. So that's my region of integration. Over here, y goes from 0 to 1, and x goes from 0 to 2, right? So clearly, these are not equal to each other, or they don't have to be equal to each other, okay? If f is 0 or constant 1 or whatever, then they end up being equal. But in general, if you don't know what f is, you cannot say that they are equal to each other. I hope it makes sense. So what then is this equal to? This is equal to, and maybe you can write down the double integral where you have the order dy dx. Now that should be a pretty simple problem. See if you can do that by pausing this video and writing down the bounds. Okay, so the answer should be pretty simple because all you're doing is switching the order. So the x goes, that's the outside variables. And so that would be from 0 to 2. And then y goes from 0 to 1, right? And that's all you have to do. So that's equal to this. All right, so what I was going to say earlier, just a few minutes ago, is just a couple of notes. You know, when you integrate 1, okay, so it's, you can write 1 here, I guess, but this is the same as a to b dx. Okay, you know what that is? I hope you know. This is, of course, if you want to write this, using the antiderivative, I mean, this is what happens. It's b minus a, right? You don't really need this. And this is really the length of the interval. And this is an important thing. And of course, you say, well, yeah, of course, I knew that, right? But what happens if you take the double integral, right? So this is the way you write this. If you are talking about the double integral over the region R, we just go ahead and write the double integral like this, right? Two of them right next to each other, and then put R over both of these. Okay, so this means the double integral over the region R of 1 dA. So what happens when you integrate 1? Okay, well, in the same way that you get the area here, I mean, basically what we are saying is, you have, let me illustrate this, okay? So when you are talking about this integral, integrating 1, all you are doing is you are integrating from a to b the function whose height is 1, right? And of course, if the height is 1, the area turns out to be exactly b minus a times 1, which is b minus a, and that's why you get the length, right? So think about this, in this case, what's going on here? In this case, what you're saying is you have this region R, right? And 1 is the height of the function, which is like, just make this 1 inch thick, okay? So think of like a piece of meat, like your favorite steak. Okay, it's 1 inch thick. That sounds really good, right? So that piece of meat, 1 inch thick uniformly, the volume is exactly the same as the area of R, right? Because the area of R times 1 is the volume. It's still the area. So this represents the area of R. And in fact, you probably never saw the definition of area, right? I mean, you learned about areas when you were in elementary school, probably, but you never learned what the definition of area is. This really is a definition of area. Area is the double integral of the region R, okay? And so in the same way, since we are in 2 dimensions, let's just go to the next one, okay? If you have this solid E, okay, here's a solid E. If you have a solid E, and if you have 1 dA, what does this mean? Okay, again, I can't make this thicker by 1 because this is already in 3 dimensions. If you add, if you are trying to make this thickened, you have to have a 4th dimension that you need to visualize, which we can't. If you can visualize your 4th dimension, please let me know, and you and I will write a book and be famous. All right. But anyway, you can do that. You can visualize it. But in the same way as we talked about this, okay, this is dV. All you're doing is defining the volume. All right. So if you have 1 as the integrand, okay, think of that as if it's a single integral, it's the length of the interval. If it's a double integral, it's the region, it's the area of the region. If it's a triple integral, it is the volume of E. Okay, that's what these things represent. So keep this in mind as you move forward. All right, going back to the original question here, let's do some integrals. Oh, maybe I should do one more thing. All right, so what happens then? Here's an example. What happens if I say R3 dA? Okay, so you can interpret this in 2 different ways. Okay, you can certainly take out 3, right? And so this is 3 times the area of R. That's certainly a way to think about this, okay? Or you can think of this as, what is that? It's the region R, and then you have 3 as the value of the function at every point. Okay, so what are we talking about? Well, that would be like saying we have a region R, and every point in the region has the 3 as the z value, the y f of xy, right? So you can think of this as a volume of the cylinder, solid cylinder, over the region R, right? Of height 3. And of course, that's the same thing. I mean, if you have something whose height is 3 uniformly or constantly, then the volume of that will be 3 times the area of R, right? So, but this is a 2-dimensional interpretation. This is a 3-dimensional interpretation. And I just want you to know these things. This may come in handy as you visualize your integration or as you do your homework. All right, so let's do some integration, okay? I am going to do this first, 0, 1, 3, 5, dy, dx. Okay, what is this? Okay. I want you to visualize what you're trying to find, and we will calculate this, right? So that means x is between 0 and 1, right? And y is between 3 and 5. So the region that you are integrating is somewhat like this. Okay, so this is 1. X goes from 0 to 1, and y goes from 3 to 5. This is your region of integration. And of course, there is nothing here. I mean, this is, 1. I don't even have to write this one because it's just number 1. And so this would be the area of the region, right? And of course, I mean, the answer should be 2, because you can tell from this picture that it's a 2 by 1 rectangle. So the answer has to be 2, right? And the way you integrate this is, well, see, look, you do this integral first, okay? What is the integral 1 with respect to y? Well, of course, that's y. And then you go from 3 to 0, 5. This is how you integrate it, hopefully, using your fundamental theorem of calculus in calculus 1. And so this is 5 minus 3, right? And so that's 2 dx, and then you have 2x going from 0 to 1, that's 2, and then 1 minus 0. Of course, it's 2, all right? And so that's what you do if you have to integrate. So inside first, you work your way from inside out, okay? That's what you are supposed to do on these things. And by the way, if you have to rewrite this, this is equal to obviously 3, 5, 0, 1 dx dy. And if you do this in the other way, you also get 2. I'm not going to demonstrate this here, but all right. So now let's try another thing, another example. Find the integral over the region R of 2y dA. Okay, and I want you to visualize what you're trying to integrate, and you can find this answer geometrically if you are good at visualizing what this is, right? Now, I haven't told you what R is, okay? So R is what we call, and there are different ways of writing this. I would introduce you now to this way of writing. Okay, so this is called the Cartesian coordinate. Sorry, the Cartesian product. Okay, because it's an interval times an interval. And what this means, and you will see this in many books, including some in this book, probably not in this section, but what this means is this is a set of all x, y, such that x is between 0 and 2, and y is between 0 and 4. And naturally, this will be a rectangular region, all right? So what are we talking about? Okay, we're talking about this. X goes from 0 to 2 and y goes from 0 to 4. That's the region we are talking about, right? And if all of these are constants, of course you get a rectangular region. So this is called the rectangular product or Cartesian product, since Descartes is the champion of the Cartesian or rectangular coordinate system. All right, so there are two different ways of doing this, right? You can do you want to do this in dy dx order or the x dy order? I'm saying this differently. All right, so if you choose to do this in the first order, dx dy, notice here you have to write the outside bounds first. And since dy is the last thing you wrote, these numbers will go outside. And so what is the integrand here? You're integrating the function 2y, okay? And in this order, dx dy. Right, get that? This is very important. It's very important for you to know how to set up these double and triple integrals, right? So because y is outside, the bounds for y goes outside as well. And the integrand is, of course, in the middle. And you do what first? You put this part first, okay? And the way you do this, and I will show you exactly what's happening in this in just a moment. What you're doing is you're integrating this, the first part, without changing y, right? Because this is with respect to x. So just like in partial derivatives, you keep the y fixed. So think of y as a constant here. It may be hard to do because your brain thinks y is, of course, a variable, right? So think of this as a constant. So then what? You have 2y, and I mean, if this is 2, the integral or the antiderivative of 2 is, of course, 2x, right? So the antiderivative of 2y with respect to x is simply 2y times x, and where x goes from 0 to 2. Okay, that's this part of the integration process. Okay, now, of course, you can do this. You don't have to separate this, right? And so this is from 0 to 4. And you get 2y times 2 minus 0, of course, right? And then the rest is easy, right? So this is going to be 4y dy, which becomes 2y squared, going from 0 to 4. So this is 16 minus 0 times 2, that's 32. Okay, I'm going to show you what we just did. Okay, so give me a moment to draw this, and I will come back. Okay, so the integrand was f of xy is 2y, right? And that's this plane. I mean, z is equal to 2y. So when y is 4, of course, z is 8. And when y is 0, z is 0. And x doesn't matter, so you extend it in x direction. This is what the function looks like, right? And if I may add, what the integral represents is really just this, okay? So what is just this? That's this sort of a triangular prism, okay, piece, right? And it's like a half of a solid like this, where this is 2 and 4 and 8, okay? So it's half of a 2 by 4 by 8 block of wood, for instance, if you want to think in that way. Okay, does that make sense? Right? And so, so it's half of this solid. And so, of course, if you have 2 times 4 times 8, that's 64. And half of that is 32. Okay, so that's a way to get this. But what I want to focus on is the order in which we did this first. Okay, and I'll do it in the second part too. When I calculated this middle part integral, we fixed y, right? And that means we are fixing y at a certain point. Okay, let's say y is here. If you slice this block at y, you get this slice for this particular y. See that? And you can tell as y moves closer to 4, this slice gets bigger and bigger, okay? And as y moves down to 0, then this gets smaller and smaller, right? And so what you found here for y, after you did the inside integral, for y represents the area of this slice for this particular y. If y is 0, the slice is 0. Okay, if y is 4, the slice is 16. That would be 2 by 8, right? This is 8, this is 2. So that 4y represents, let me just write this down. 4y, this thing here, is the area of the y slice when you cut it this way. All right, so keep this in mind. Now also, if you decide to do this in a dy dx order, remember x goes at the end, so the 0, 2 goes at the end, and 0, 4 goes in the middle, and then 2y dy dx. All right, I'm going to do a same kind of drawing here, and I will show you what we are doing first in this. Okay, so we're about to do this. Okay, let's go ahead and do this. And this is the picture, by the way. It's the same picture as the one that you saw on top. And the way you integrate this, numerically, is you integrate this with respect to y, okay? Y is a variable, so 2y becomes y squared, right? And of course, you still have 0 to 4, but I will just write it this way. So this part here will become this. And then, of course, you integrate with respect to dx later. All right, so this becomes, what is that? It's 16 minus 0, right? Now, this 16 represents something. You know what this is? That is, remember, when you do this inside integral, x is considered a constant, okay? So I pick a constant x here, and if I slice it, I use a blue for slices. Oops, that's not blue. If you slice it at this particular x, that block, whoops, does not look like that. Let me go back and erase everything I just did. This slice becomes more like this. It's a triangular slice, okay? And it turns out, regardless of which x you slice this block at, it'll still be exactly this triangular thing. And this triangular thing, this is the x slice. And this x slice is independent of x. You can see if x is 0 or 2, you still get the same congruent triangle. And this triangle has the base 4 and height 8. And of course, 4 times 8 divided by 2 is 16. So the area of this x slice is 16 everywhere. And that's what we just found, okay? Now we integrate from 0 to 2 because you have, the volume of 2, if you go this way, this length here is 2. And so you multiply this by 2 and you get 32. Of course, that's the same answer we got here. According to Fubini, you were supposed to get the same number, so you got it. But you also recognize this as the volume of this prism type of a block of wood or block of cheese, right? And so that's what you do. And the order should not matter. Either way, you will get the same answer. All right, I have a couple more examples. So let's take a break at this point, and then I will show you the last few examples.